and meeting facilitators for tonight. Teresa Seidel is the Division Director for the Water Resources Division of the Michigan DEQ. And Tracy Katsumetti is our DEQ Southeast Michigan District Office Coordinator. Teresa and Tracy.
Good evening. So there's a couple things we want to talk to you about before we get going with the presentation. The first thing is make sure you silence your cell phones. It's an auditorium. We want to make sure everybody has an opportunity to hear what the presenters have to present this evening. But mostly, thank you for coming and getting your questions answered. This is a question session. This is not a comment session. The card you have, we ask that you, when you're thinking through the presentation today, if a question comes up, that you write it on the back of the card. Get that thought out of your mind so that you can then refocus on what the presenters are giving you information to you tonight. So please put your questions on the back of that card. Tracy and I, after the presentation, will take a short, about 15-minute break. And Tracy and I will work both sides of the room coming to you with the microphone to get your questions asked. You can either ask the question directly into the microphone, or you can move your card to the end of the aisle and Tracy and I will ask it on your behalf. Either way is fine. It's just your preference. So that's what the card is for. As I said, this is just for questions tonight. Formal comments will happen at the July 24th session and the July 25th session. So that's where you'll be able to actually get your comments regarding the reports and the analysis on the record. Tonight is just for your opportunity to get your questions answered regarding the presentation. So we're going to come through the aisles. We'll just kind of meet you halfway. If we can't get to you, if we ask you to come to the edge of the aisle so that we can get your question. And then just be a short opportunity for you to get one question at a time answered. The kind of play sheet, the dark blue cardstock sheet, has kind of the ground rules for today. We ask that you be courteous to your fellow listeners and presenters and give them an opportunity to give you the information. And then you can ask your questions following that, and Tracy and I will try and facilitate and get everybody's questions answered as timely as possible. One question at a time. If there's an opportunity for more questions at the end, we'll allow for that, but we do have a time constraint with the facility, so we want to make sure we get everything answered as quickly as possible and then as fulfilled as possible for you also. Any questions on that before we get going back with Matt? All right, have a great night.
Thank you, Teresa. At this time, I'd like to introduce Pat Veith, Senior Vice President at Dynamic Risk, to introduce his team and begin the presentation.
Thank you, Matt. Welcome, everybody, both here at Holt Auditorium and across the internet. Over the past year, Dynamic Risk has undertaken a study to evaluate the Line 5 pipeline that crosses the Straits of Mackinac and evaluate alternatives from the perspective of operational risk and socioeconomic impacts for each of those alternatives. Dynamic Risk was selected by the state of Michigan to undertake this study based upon the experience of our project team. As Matt mentioned, I'm Pat Veith with Dynamic Risk, where I'm the executive sponsor for this project. I'm the Senior Vice President of our Technical Services Group at Dynamic Risk, and I have 30 years of experience working for stakeholders across the pipeline industry. This has included research, technology development, codes and standards development, and engineering assessments covering most aspects of pipeline integrity. I would like to recognize our colleagues that supported this project from the Office of the Attorney General, the Department of Natural Resources, Department of Environmental Quality, and Agency for Energy. Thank you for your support. Before we move on, I'd like to show for you that may not have gone through the whole report. This is a copy of the report for those that didn't print it, a copy of the attachments, and a copy of the appendices. We're not going to be doing a page turn this evening. However, I do share that just to demonstrate the amount of work and backup information that went into this report, and we'll be describing from a high level the contents of that report. Next, I would like to introduce the companies and the personnel that have supported this project, the Dynamic Risk project team. The first company is Dynamic Risk, of which I'm a part of, and we have provided technical support to the pipeline industry stakeholders for the past 20 years, with a primary focus on risk and integrity management. For this project, Dynamic Risk provided overall program management and quantitative pipeline risk analyses. The members of the Dynamic Risk team here today are Mr. Jim Myhill. Jim is the chief engineer and is the principal investigator for this project. Jim brings 33 years of experience on engineering assessments and risk assessments for planned and operating pipeline networks. Next, Ms. Naseem Tarani is a senior integrity engineer and has 10 years of experience with a primary focus on consequence analyses. Third, Mr. Bill Ho. He served as the project manager for this project, where he coordinated all aspects of the project execution and information management. We also brought in several partners to execute this project, given the depth and breadth of experience that was required to do so. One of our co-parts is DHI, and they're global leader and widely recognized as the top experts in modeling effects of oil spills in marine environments. They maintain approximately 1,100 staff operating in more than 140 countries. For this project, DHI's focus was the spill modeling. Dale Kerper, seated toward the end there, has more than 28 years of experience performing engineering studies in the marine and coastal environments using advanced numerical modeling techniques. The next organization is H.J. Rutenbeek Resources Consulting, and they've provided independent, scientifically sound policy advice in over 70 countries for socioeconomic assessments, economic risk management, cost-benefit analysis, and the economic valuation of environmental impacts. Dr. Jack Rutenbeek has 35 years of experience, is an independent consultant and researcher. His work has spanned projects for national governments, aid and lending agencies, the private sector, and international environmental NGOs. The next organization is Kelly Geotechnical, where they provide geotechnical engineering related to terrain analysis, geological hazard assessments, geotechnical design, as well as construction input for a range of projects. For this project, Shane Kelly brought forward his expertise as a senior geotechnical engineer with 20 years of experience regarding terrain analysis, geological hazard assessments, geotechnical design, and construction. Our last partner in this study is Stantec. They're an international professional services organization specializing in design and consulting with over 22,000 employees in over 400 locations internationally. For this project, Stantec evaluated the feasibility of routing and configuration of each of the alternatives and established the cost basis for each. Mr. Jim Penny has over 25 years of experience in the oil and gas industry, specializing in detailed engineering and construction management for the pipeline projects. This comprises the core Dynamic Risk team that executed this project. Our draft final report, Alternatives Analysis for the Straits Pipeline, was released last week. This report was over 1,000 pages in length and described the approach to each of the analyses, the assumptions, and the presentation of the results. As such, this report is lengthy to ensure full transparency into the analysis and the associated results that go with those. As described in our statement of work that we will cover later, we've produced a result that can be used by all stakeholders to evaluate each of the alternatives addressed. In accordance with our scope of work, we have not made any recommendations. The Dynamic Risk Project team was selected by the state of Michigan based upon its extensive experience and domain knowledge that have been relied upon to effectively execute this project. Just this core team today presents over 150 years of collective international experience. For every project that we undertake, including this project, bringing forward an objective assessment is core to our standards of practice. This objectivity, along with the transparency into our analyses, have provided the state with an independent and objective assessment that has relied upon facts and the engineering analyses outlined in our report. We've produced this factual report based on science and engineering, and from the beginning of this project, had no preconceived outcomes. We all recognize that engineering assessments are about calculations, and as such, we have documented each step. It is therefore left to each stakeholder to rely upon the facts presented in the report, and as such, provide risk-informed decisions for any of the actions that may be considered. This is an overview of our project team. So this is the objective of the project that we undertook, and I think it's important to characterize some of the key elements. That it's really to provide the state of Michigan and other interested parties with an independent, comprehensive analysis. And we've done that by producing our report that documents each step of our process. It's been provided to the extent possible each alternative to promote the public health, safety, and welfare that protects the public trust resources of the Great Lakes. As I mentioned in my opening remarks, the work does not include a recommendation by us, but instead it can be used by the state and other interested parties in making decisions about the future of the Straits Pipeline. Next, what I'd like to do is to give a real high-level overview of what we mean by Line 5. Line 5 extends from Superior, Wisconsin, over to Marysville, Michigan, Sarnia, Ontario. There are a couple of key locations along this pipeline that will be discussed. The first is the Rapid River, where a depropanizer extracts propane from the NGLs and supplies propane to the Upper Peninsula. Next is the Straits, which is a 4.5-mile crossing and is the focus of our analysis. Next is Lewiston, Michigan, which is an injection point for Michigan producers, and they inject into Line 5. And lastly, Marysville, Michigan, where some of the crude is distributed to refineries, such as Marathon and the Toledo refineries. So that gives a footprint of a lot of the area that we will be discussing today, and you hear throughout our presentation reference to some of these locations and the effect that they have on our analyses. As we move into the presentation, this is the outline that we will be following. You'll see as we progress through that, we'll keep track so that you can tell where we are in this whole process, and we'll characterize it throughout our discussion. So without further ado, I'll turn it over to Mr. Jim Myhill, and he will be presenting on the feasibility analyses.
Thanks, Pat. I just want to forewarn you, you'll be seeing me a couple of times this evening. First, I'm going to be speaking about the feasibility analysis, in which I'll talk about each of the alternatives that we were tasked to investigate. And then later on, grayed out in this slide here is the spill risk analysis. And part of the focus, of course, of all of this is to evaluate the risk of each of the alternatives, including the existing Straits crossings. And so I'll sit down after this feasibility analysis section and pop up again later on and talk about the risk analysis. So to talk about feasibility, first of all, I need to introduce the alternatives. And starting with these alternatives were given alternative numbers in no particular order. So I don't want you to perceive that alternative 1 has the number 1 means anything. There's no order whatsoever with respect to how these were numbered. These were the numbers that were given to us in the scope of work. So alternative 1 is a new pipeline route. And for this, we really investigated 3 routes. There was a north route, you can see on this map here, that evaluated the feasibility of a new pipeline going north of Lake Superior and coming down ultimately into southern Ontario and coming then west into Sarnia through that routing there. The central route provided a parallel route to Line 5 to St. Ignace, and the new involved a new route across the St. Mary's River in Sault Ste. Marie. Ultimately, that central route was discarded because what we were tasked with respect to this particular alternative was that the alternative new pipeline route could not cross the open waters of the Great Lakes, and so that central route was automatically discarded. The southern route goes down south of Chicago and bypasses the straits by going around Lake Michigan. In all cases, the new pipeline routes that were evaluated were 30-inch diameter pipelines with an operating pressure of 1440 psi, which is considerably higher than the current operating pressure, but nevertheless it reflects a more economical design, and for that purpose we evaluated that as a set of criteria. I have to move my computer a little bit closer, I'm having trouble seeing. Alternative 2 is to utilize existing infrastructure, and that alternative investigated whether or not there would be spare capacity on existing pipeline infrastructure that could be utilized to ship natural gas liquids and oil that is currently shipped on Line 5, and whether or not we could use that spare capacity to get from point A to point B. Basically, what we found, to just give you an overview, is that there was very limited spare capacity either on Enbridge's existing system or on third-party capacity as well. And really, what we found was that in all cases, there was not existing infrastructure that would enable us to get the necessary products from Superior to Sarnia without building new pipeline infrastructure. In that respect, it wasn't really materially different from Alternative 1, building a new pipeline. Alternative 3 was investigation of other transportation methods. And we looked at 3 alternative transportation methods. One was shipping from Superior to Sarnia. That's problematic because there's no year-round shipping through the Soo locks, of course. They're down for 2 or 3 months in the wintertime. And so that means that we need to build storage capacity in order to stockpile the products over the period of time that the locks are down. The second alternative was to look at road trucking from Superior to Sarnia, and that would have involved a fleet of about 3,200 trucks, loading trucks at a rate of something like 1 every 40 seconds or so, and it would have involved heavy load on existing transportation infrastructure. The third option is rail from Superior to Sarnia. Again, that's a very extensive development of existing rail infrastructure, but we were able to flesh out existing rail routes that would enable oil to be transported from Superior to Sarnia. Nevertheless, what it involves is 9 unit trains worth of oil. Unit trains are large, dedicated trains that ship only one product. So roughly 100 cars in a unit train, and each day you'd be shipping about 9 unit trains from Superior to Sarnia. Annually, you'd be looking at transporting about 200 million barrels of oil, which in terms of existing shipments within the U.S., that represents about 2/3 of all oil that's currently being shipped by rail within the United States. And by the way, just 10 years ago, the amount of oil that would have been shipped at that period of time was about 50 times less than the amount that we're talking about shipping in this case. So pretty extensive rail infrastructure development and utilization of rail tracks. In all cases, there's storage tanks required in order to accommodate the necessary storage in the event that there's outages along the rail facilities. Alternative 4. Under Alternative 4, we were tasked with providing a hypothetical replacement option for the Straits pipeline, utilizing best practices technologies. And so Alternative 4A looks at conventional trench installation. It's 4.1 miles in length, goes through about 230 feet of water, 30-inch single pipeline, 30-inch, 0.812 inches in wall thickness, material grade X65, which operates at about 20% of its yield strength. For the purposes of fleshing out this analysis, we considered that that hypothetical pipeline would be coated with 3-layer composite coating and that it would be buried throughout its crossing. So about 9 feet of burial depth near shore and 3 feet of burial elsewhere. Alternative 4B is a straits replacement in the form of a tunnel. And again, a hypothetical crossing. On this drawing, you can see where the hypothetical crossing we investigated is. And under the design that was developed, we looked at tunneling by means of tunnel boring machine. And immediately following the tunnel boring machine, the construction would involve segmented concrete liners that would follow the tunnel boring machine and line the rock walls. You'd be drilling through rock the entire crossing. You'd then be grouting the formation, the rock formation, to prevent leakage and to ensure sound rock walls all around. Similar pipe spec, 30-inch 812 wall, grade X65, and again 20% of yield strength. We'd still have coating on it, 3-layer composite coating, and the pipe would be assembled on shore and advanced through the tunnel, exiting from the shaft. In this case, what we looked at is sealing the annulus around the pipeline, between the pipeline and the walls of the tunnel, with low permeability, high strength grout. And now there's a variety of ways of doing tunnels. This is the way that we looked at. Now I'm skipping over alternative 5. Alternative 5 is actually the existing straits crossing, and we fully evaluated the existing straits crossing in terms of the risk, but nevertheless, the alternatives to the existing are 1 through to 6, exclusive of 5. And alternative 6 is decommissioning and abandoning the straits. And so of course, with respect to decommissioning and abandonment, there is no operating risk. If you don't have a pipeline, and you don't have operating risk, but there are financial and economic impacts, and so this is what we investigated fully in that alternative. With respect to the limitations of using existing segments of Line 5, both in the northwest and the southeast, in order to transport natural gas liquids in the northwest and Michigan-produced oil in the southeast, we ran into some limitations in the northwest with respect to that, because the existing pipeline in the northwest is 30 inches in diameter. The amount of natural gas liquids that are extracted for use in the Upper Peninsula are relatively limited. And what happens essentially when you try to put such a small amount of throughput through such a large pipeline is that you run into operational constraints that makes it operationally unfeasible. Really what you would need to do is replace the northwest leg with a 4-inch pipeline to carry just natural gas liquids to serve the UT market. And in the southeast portion, to take Michigan-produced oil to market, you'd need only an 8-inch pipeline. In the economic evaluation of this alternative, we looked at, we had to establish financial costs associated with it, and so we had to come up with a decommissioning strategy. And that decommissioning strategy was developed per the requirements of the United States Code of Federal Regulations and Industry Recommended Practices. And basically, what that means is that in cultivated, forested, urban lands and wetlands and river crossings, you would abandon that in place, and there's 527 miles of that. With respect to road and trail crossings, again, you would abandon the pipe in place, and there's a total of 13 miles associated with that. And water crossings themselves, 5 miles of that. So the process of abandonment would involve cleaning the pipe and purging of hydrocarbons. You'd have transitions to above ground would be cut, and you'd remove all above ground equipment. So that's an overview of the alternatives to the existing straits that we investigated as part of this analysis. And part of our work was to establish the feasibility of all of this. And in short, just by way of summary, alternative one was considered to be feasible, the new pipeline route. We fully evaluated the new pipeline route. The most cost-effective of that was the southern route going through down south of Chicago. Alternative two was to utilize pre-existing alternative pipeline infrastructure. That was found to be infeasible because there is no existing pipeline infrastructure with spare capacity that would enable us to move volumes of product from Superior through to Sarnia. Alternative three was really three, if you recall, three subparts to alternative three. Alternative three looked at alternative transportation methods, with one being water transport, the other one being truck transport, and the third one being rail transport. Of the three, really only rail was considered to be feasible. In particular, the water transport would require a large fleet of ships along with a significant amount of storage, if you recall, because of the Soo locks being closed seasonally. And that would involve a total of about $4.3 billion worth of infrastructure combined between the storage required along with the ships. The trucks, you'd be loading and unloading one truck every 40 seconds and putting it on state highways. And that would present a tremendous strain to existing infrastructure and to road safety, and it was just deemed to be impractical, and it was not further developed in the economic analysis or in the risk analysis. The rail option was, however, considered viable, hypothetically at least, and so we fully developed that as part of the economic analysis and the risk analysis. Alternative four, replace the Straits crossing. Again, we have two hypothetical replacement strategies, one putting in a dedicated trenched crossing, the other one being a tunnel crossing. We evaluated both. Alternative five is to maintain the existing Straits crossing. We looked at the risk of doing that and the cost associated with operating. And finally, alternative six, decommissioning, again, feasible, and we, although there are no risks, no operating risks associated with that alternative, we did investigate the financial implications of doing that. So that's, in a nutshell, an overview of the feasibility analysis. I'm going to call on Jack Rutenbeek to come up and talk about components of the analysis of economic analysis. Jack, you want to put this up here? I know you can see.
That's okay. I'll try. Good evening, everyone. I'm Jack Rutenbeek. Bear with me for a moment while I organize my long-distance viewing. I'll linger on the slide for a moment because it does show three of the parts of the economic analyses which I'm going to cover in the next 7 or 8 slides. But before I cover those slides, I'd like to just give a little bit of background to each of these and to characterize some of these analyses that we did. First of all, the team went through a design-based cost estimates, which were done consistently using current construction prices, current labor prices, current this, current that, as they occur in the Great Lakes region. In some cases, of course, they were for northern Canada, but in other places they were for the southern routes, which were, of course, American pricing in the Midwest. And as all of our alternatives that we're considering here are in the U.S. Midwest, the important thing to keep in mind is that for this comparative analysis, we used a consistent set of assumptions for inflation and so forth that are all documented in the report. I'm not going to bore you with all of those assumptions, but you can look them up within the 1,000 pages that were in that Pat showed earlier. So those cost estimates, because we are comparing different alternatives, it's very important to keep them on common ground, and that's what we did. The next two types of economic analyses we did, I'll characterize as economic feasibility and socioeconomic impacts. Now, the economic feasibility part of this is to take a look at the relative costs to do similar thing. Now, the relative costs are the relative capital and operating costs, and the similar things are to transport 540,000 barrels a day from Superior to the Marysville and Sarnia area. So, of that 540,000 barrels a day, about 1/6 is a natural gas liquid stream. So, all of these alternatives that we just considered, with the exception of abandonment, of course, somehow involve the transport of those liquids across this system through Line 5 or through these alternatives. So that's a common denominator in looking at the economic feasibility. Again, it permits a comparison between these different alternatives. The other one is what we call the socioeconomic impacts, and some of them are what at this stage we call fairly quantifiable impacts, the economic impacts in terms of jobs and income and government revenue from each of these, and the others are somewhat softer. They're social impact assessments that might happen for a facilities type of project. I want to make sure that we recall that this part of the analysis has to do with facilities, construction, and operation. And the analyses that we're doing, certainly for the socioeconomics, focus on Michigan. That said, I also want to underline the difference between the economic feasibility, which we'll see in a moment we talk about in terms of cost effectiveness, and the socioeconomic impacts, which we look at in terms of jobs and income and so forth. These two are sometimes seen as two heads of a similar coin. They're both economic analyses, but in some cases, when you have something that's very, very inexpensive to run, that is very what we call cost effective or efficient, it doesn't necessarily create a lot of economic impacts in terms of jobs and earnings, and that's simply because there's not a lot of money being spent. On the other hand, projects that do involve very high costs, such as the routing, which was shown for the northern pipeline through Canada, it's very expensive, and that would have created fairly large economic impacts within the region, not in Michigan, but it would have also been very expensive, so not very cost effective. With that, I'll now bounce to the very few slides I have on each of these. The cost effectiveness analysis. This slide shows a few things. It shows how the capital and operating costs from each of these alternatives is turned into a single measure of cost effectiveness, which we characterize as a dollar per barrel cost. So, for example, I'll just look at the first line without, excuse me. I'll just look at this line here, which is the rail alternative. That involves about $900 million of expenditures, of which none are in Michigan at the capital stage. That's because the design of that alternative required new investments in Superior and new investments in Sarnia, but the railway itself was using existing lines and corridors through Michigan, so there's very high operating costs on the entire system, but the only amount of money that really gets spent in Michigan is 15% of the operating costs. Together, all of that comes to what we call a levelized cost in terms of dollars per barrel of about $6.50. Okay, so that's neither good nor bad, it's just what it is. To put that into perspective, the current system, which is the Lakehead system of transporting oil from Superior to Sarnia area, which includes Marysville, is about $1.50. So right now, shippers are paying about $1.50 to get their product from one side of the system to the other side of the system. This would cost them about $6.50 to do the rail. Similarly, the next alternative, which is a new pipeline, is costing about $2 billion. Of that $2 billion, about 30%, or 29% to be more precise, would be anticipated to be spent in Michigan. That's because the corridor goes through Indiana, Illinois, and Wisconsin, and about 30% of the mileage is in Michigan. There are a certain number of pump stations, there's construction spreads, and so forth. These occur in Michigan. Similarly, the operating costs for that are about $225 million in the first year, and they decline to about $165 million steady state after 10 years. It's characteristic of these pipelines that there are higher costs of operation for the first few years. This all translates over that almost 200 million barrels a year, or 540,000 barrels a day, into about $1.60 per barrel over the long term. Similarly, for the new trench crossing and the new tunnel crossing, these two respectively have capital costs anticipated to be $27 million and $153 million. And I'll come back to the operating costs in a moment. Both of those are spent entirely in Michigan for estimating the operating impact. The operating costs of those are not much different than they are of the current Line 5. You don't see this in the slide here, but the Line 5 current operating costs are just under $100 million a year. This includes a certain amount of imputed costs of the fixed costs of the system, as well as operating costs like wages for operating it. It includes electricity costs for the pumping requirements of the various stations and so forth. So that Line 5 cost is also the same as what it would be for these two alternatives under Alternative 4. Finally, Alternative 6, and I should back up a minute here. Those two alternatives translate to an incremental cost of about 1 cent a barrel to about 5 cents a barrel compared to the current tariff. Those are in addition to what the current cost of operations would be, of operation and return on capital. Now let's go to the last alternative, which is the abandonment of Line 5, and it was explained earlier what that entails. A lot of that is in place, but that cost comes to about $212 million of capital costs. There are very moderate operating costs in reality. We haven't estimated them specifically here. They're relatively low in the grand scheme of things, but there's a certain amount of monitoring that normally goes on with an abandoned pipeline for some period of time. But the main contribution to the cost is going to be the capital, which translated over whatever alternative stream is, it works out to about 7 cents a barrel. That was the feasibility side of it. I just want to go to the socioeconomic impacts now in terms of the job side of it and income side of it. Our study used a certain method that models the economic impacts, but just by way of background, if you look at the report, you'll see that we've defined various areas of interest which are driven by the prosperity regions. Line 5 goes through about 19 counties, and those are the ones listed on the left-hand side of that. They go through prosperity regions 1, 2, 3, 5, and 6. And in a few places in the report, you will see those characterized. The report does distinguish between impacts in Michigan and impacts within these areas of interest through the corridor of prosperity regions, as well as the corridor of counties. And if you look through the multitude of appendices and attachments, you will find information on all of those corridors, on all of those counties that are intersected by line 5, as well as the corridors that are intersected by the rail and the southern pipeline alternative, which are also depicted in this slide. For today, I'm just going to focus on the Michigan impacts because those are in fact the most robust and most stable because of the modeling that we were undertaking. The socioeconomic impacts were calculated using multipliers from the RIMS 2 model. The RIMS 2 model is a model of the United States which permits regionalization to any area that you wish. The areas that we chose were, of course, Michigan as a whole, plus the pipeline corridors, plus the prosperity region corridors that we just looked at. The Michigan impacts are the most robust because these types of models, they're called linear models, are most reliable for larger areas basically, and that has to do with how economic impacts leak outside of a region. And if you're looking at a very small region, like a county, most of the spending doesn't happen in the county. When people live in Livingston or wherever they might live, they're going to buy things and spend their money elsewhere too. So the actual model is more stable when you look at a larger area. So the Michigan impacts are quite robust. The model actually defines, and the report shows impacts that are called direct, indirect, and induced. Briefly, the direct impacts are whatever happens from the initial round of spending. The indirect happens because whoever spends that money in the first place, and certain suppliers, those suppliers also have to hire other suppliers to supply whatever they're billing, and they need to employ labor. So that's the indirect round. And the induced round happens when people who are part of the inputs, they're the wage earners, take that money and go out and spend it on things. So these 3 rounds are all included in the bottom line numbers I'm presenting to you this evening. If you want to see how those break down, you'll have to go to these thousands of pages and see that. But all of those are actually included in there. That's how we've used this model RIMS 2 to look at the jobs, the earnings, the output of both the operating and the capital expenditures. We have our own model for government revenue, which is driven off some of the income impacts of that because government gets its money from things like sales taxes and personal income taxes, and as your earnings go up, then state revenues and government revenues will go up through a mechanism that is linked to your incomes. State also receives income from potentially pipeline taxes and rail taxes, and those are also estimated and included within these numbers. And again, I'd like to repeat that the estimates are most robust for larger regions, and they're also more robust for operating impacts because operations tend to be embedded within the economy, whereas Construction, some people call those impacts more like a flash in the pan, so that they happen once and there are some impacts over a year or two and there's a bit of a ripple effect perhaps. The qualitative analyses that we did were the social impact assessments, and we did what would be regarded by best practices as a screening assessment. The study relied entirely upon secondary information. We didn't go out into communities and ask what they would think if they had a train running through their backyard, or a new pipeline built next door, or a new construction work camp for a trench or a tunnel, or how their boating might be impacted if there was more activity from the facility's construction. That is something that would happen at a much later stage of design. It would happen with public consultations. Those public consultations would normally identify concerns and help in identification of mitigation measures. This type of screening assessment is to give some guidance to that eventual public process, and it identifies early on some of the things that might be concerns of local residents if some of these facilities applications in the alternatives went ahead. For example, we all know that there are congestion impacts from construction, whether that's building a road or building a pipeline or building anything. There can be traffic congestion, and that's usually a concern. We identified any of a concern perhaps with the projects in the straits, the trench or the tunnel alternatives, to the extent that that might happen during a busy tourism season. That could place additional demands on housing and worker availability during those periods. These are the types of concerns that come up. And so the idea of this screening style of matrix is to qualitatively assess things like that, the dust from construction, the noise from trains. That's all part of a preliminary screening. If you look within the report, there's other information which gives you baseline information on every county that these facilities would potentially go through, hypothetically. And it also gives land use in all of these areas, which help us identify later in the skill analyses what are potentially high consequence areas. And it also identifies potential tribal interests in the use of resources in the lakes or in the area, in any of these terrestrial areas of Michigan through which these alternatives go. The actual number crunching, in effect, started with the cost estimates, and I'm not going to go through every alternative. This is just one example for alternative one. It shows how we get from the impacts, from the initial expenditures and the capital costs to the eventual results. And what we do is we take a cost of, in this case, almost $2 billion across 4 states. We look at the design, we look at the number of construction spreads, and say, oh, of this, about $586 million is going to actually happen in Michigan. Now, some of that may happen in Michigan, but there's no way Michigan can supply it. Michigan is not a supplier of 30-inch diameter pipe, or it isn't right now. So some of that needs to be purchased elsewhere. What's left is in this particular case about $435 million, which is spent inside Michigan. And using the multipliers and the various categories of goods that we know from the design are purchased, we conclude that over a period of about 5 years in this case, because that's how long this particular construction project goes, it would generate just over 8,000 jobs, about $370 million in earnings, and about $1.3 billion in output, which is sort of like a GDP measure. Sorry, that's the output measure. That's the output measure. The value added complements that as part of the measures. The amount of revenue out of state that the state would get from that increased labor income, mainly in various taxes, is just under $18 million. I am not going to go through every single one of those projects that way, but this is a summary of those. Of course, the alternative, this just looks at the construction period. In the case of rail transport, nothing really happens in Michigan from that, because as I noted previously, the construction is all outside of state. A new pipeline, we just covered that. The two straits alternatives under alternative 4 of the trench or the tunnel are creating a certain number of jobs, which is somewhat proportional to the amount of expenditures and the capital costs of each of those categories. There are differences. They're not directly proportional because they will require different things and different types of inputs. The alternative 6, which is the full abandonment of Line 5, for $212 million, as you'll recall, generates somewhat over 2,000 jobs in Michigan, and it generates about $100 million in earnings and something just under $5 million in government revenues. That just happens once, remember. It's during the abandonment period. Finally, the operations are persistent. The difference between this slide and the previous slide is that all the numbers are dollars per year here, whereas the previous slide just said dollars. So the dollars per year for the rail transport, a lot is actually spent on rail, as you'll recall. It's a very expensive alternative, so it does generate quite a few jobs, and these are just in Michigan. It's about 1,200 jobs. The government revenue, we estimate somewhere around $12 million a year. The pipeline alternative is about 400 jobs. That's a southern pipeline, and a proportionate number of earnings and output. The crossings are, recall that this came from the $95 million of expenditures every single year on Line 5, of which about 83 million are in Michigan, we estimate. That generates just over 900 jobs in the direct, indirect, and induced. Breakdowns are in the report. And about $45 million in earnings, and somewhere between $7 and $9 million in government revenue. The persistent impacts of operating expenditures on the abandonment alternative are zero, because as you'll recall, there were fairly few ongoing operational costs associated with abandonment. That ends this part of the facilities. I'll later address again parts of the spill costs in the risk analysis. And the risk analysis for that, I will turn it back over to Jim.
My wife has been telling me that I need new glasses, and I've been obstinately refusing to believe her until now. Okay, the next thing that we're getting into here is the spill risk analysis. And for each of the alternatives that Jack just walked you through, and for which he explained how the economic impacts of each alternative were calculated, we also were tasked with estimating operational risk for each alternative. Just very succinctly, the definition of risk that perhaps I've run into that I like the best is the chance of loss. That's perhaps the most succinct definition I've heard. But the chance of loss really involves two different things. Chance implies there's uncertainty or a probability of occurrence, and loss implies consequence. And so when we're talking about operational risk, by and large here, what we're talking about is the probability of having a spill. And so each one of these alternatives is a certain risk associated with it. By way of example, certainly the existing straits crossing pipelines have the potential on an annualized basis for having a spill, and that spill in turn has certain consequences associated with it. Similarly, the rail alternative is associated with a certain operational chance of having a derailment and spills, and the consequences associated with that alternative. So for each one of the alternatives, there is an operational risk, with the exception of the abandonment and decommissioning, for which there's no operational risk. What we did is, and what we were tasked to do, is look at the existing risk of a base case. And for this case, in this case, the base case is the twin 20-inch crossings of the Straits of Mackinac. And we looked at what's the probability on an annualized basis of having a loss of containment, a spill into the Straits, and furthermore, what's the consequences, both environmental, health and safety, as well as economic consequences associated with that sort of a spill. That was our base case, and for each alternative, in order to compare the alternative to the existing status quo, we similarly did a risk assessment for each alternative. What I'm going to go through over the course of the next several slides is a description of how we went about doing all of this, and it involves several steps. So for the existing Straits crossing, what it involved was we started out with a threat assessment, and I'll describe that in greater detail, but essentially what the threat assessment does is it evaluates all the design materials, operating parameters, environmental parameters, for all the potential ways that loss of containment could happen, all the ways the pipeline could develop a hole or a rupture. And we evaluate the vulnerability to each one of those threats and their threat mechanisms, and establish which ones are viable and which ones are considered to be second order threats. So threats that are far below the estimation capability of the primary threats. So there's going to be primary threats and secondary threats coming out of that. Based on the primary threats, then, we come up with spill probability assessment. So for each threat, there's going to be a failure mechanism associated with that threat, from which we can anticipate what the hole size is going to be. And from that, we can then come up with a spill release that's attached to that hole size. That then gets into the consequence side of things. And we have to bear in mind that there's two products. There's oil and there's NGLs, natural gas liquids. They have two very different impacts that we needed to investigate, with oil being primarily an environmental consequence and NGLs being primarily a safety consequence. And we got into evaluating those as well. We characterized risk in terms of safety risk, environmental risk, and economic impact risk. Ultimately, and I'm circling back to a point that I skipped over, as part of all of this, we performed an evaluation of the safe and reliable operating life of the existing Straits pipelines, and so I'm going to talk about that as well. So starting with the failure probability of the existing crossing, I'm not going to get into the detail for all the alternatives, just because it's a very detailed, long description to do this for every alternative, but I will get into a lot of detail on the existing crossing. So again, we started with the threat assessment, and there is a best practice approach, an industry standard best practice approach for how you perform these threat assessments, and these involve ASME documents as well as other industry standard documents that we followed in order to classify threats and evaluate the threat attributes for each threat, and ultimately to come up with an understanding of the vulnerability to each threat. So those threats that are characterized as principal threats are characterized as such because they have significant vulnerability. They have the potential to provide the most significant contributions to overall failure probability. And for those threats, we assign failure modes and associated with both leak and rupture as appropriate. The secondary threats are characterized as such because they're deemed to have relatively insignificant vulnerability, particularly in comparison to the principal threats. That the principal threats, far and away, dominate the failure probability of the pipeline. So they're only contributing to overall threat likelihood or failure probability likelihood at second order levels, and typically orders of magnitude below those of the principal threats. The probability analysis that we undertook was a quantitative analysis, and in that respect, we didn't characterize failure probability as high, low, or medium, but rather we came up with numbers so that you could establish what's the frequency or the likelihood of having these failures occur. There's a few different methods of arriving at quantitative estimates of failure probability. They get very, very advanced, some of them. Some of them involve what's called reliability methods, in which you start with a failure model, which defines a limit state or the point at which loss of containment occurs. And that's basically a mathematical model. And to that model, we attach probability density functions, which is a fancy way of saying we attach uncertainty to each of the input variables that enables you to calculate the likelihood of failure. Beyond that, there are logical methods such as event trees, and there are other methods that involve an evaluation of incident data. Industry incident data is maintained in the United States by the Office of Pipeline Safety, a division of the Department of Transportation. And they provide a good basis for doing that sort of industry incident data-based evaluation of failure likelihood. So starting with the threat assessment approach, we began with API 1160, which is an industry standard practice document called Managing System Integrity for Hazardous Liquids Pipelines. And we augmented that with ASME B31.8S Appendix A. And both of those documents provide a basis and a framework for doing this. And there are, for hazardous liquids pipelines, of which Line 5 is characterized as such, there are considered to be 12 different threat categories. And I can go through them very briefly. Some threat categories are time dependent, in which case the likelihood of failure increases with time because they involve degradation mechanisms. And in that class are external corrosion, internal corrosion, selective seam corrosion, and stress corrosion cracking. These are all time dependent failure mechanisms. There is manufacturing defects, which can be time dependent, particularly if they get acted upon by means of cyclic forces, in which case the teeth can take hold, and that can, in that circumstance, be time dependent, but it's not always considered time dependent. Construction or fabrication defects are things such as girth weld defects or dents, which can, if they went into service in such a state that the defect was near critical, near close to failure, then over time the pipeline can advance to a failure state. You can have a failure due to a girth weld or to a dent. And again, fatigue can play a role in that. Equipment failure involves non-pipe equipment, so flanges, valves, things that contain product but are not pipe. And for the straits crossing segment, it's all pipe. Immediate failure due to mechanical damage. That's conventionally on onshore pipelines. When we talk about immediate failure due to mechanical damage, what we normally associate with that is inadvertent interaction with a backhoe or some form of excavating equipment. It's one of the biggest causes of failure, and in fact, in some jurisdictions, it is the biggest cause of failure. Of course, in the Straits of Mackinac, there are no excavators. However, the Straits of Mackinac are a busy shipping channel, and so this threat is really dominated by the potential for having inadvertent deployment and interaction of the pipeline with an anchor, a cargo vessel anchor. Time-dependent failure due to resident mechanical damage is again, if you have subcritical damage due to mechanical damage, it doesn't cause failure immediately. It can still cause failure over time in the presence of cyclic forces, but you need to have some resident damage to begin with in order for that to take place. Incorrect operations. Most commonly, incorrect operations failures involve failures on a pipeline system due to wrong practices or procedures. Often when a pipeline system is being maintained or operated in some fashion, something can happen, and as a result, somebody makes a mistake and results in a leak. So that's a separate threat mechanism. Whether an outside force is what is loosely characterized for the purposes of this investigation as geotechnical threats. Under geotechnical threats, we would consider things such as potential for landslides, for washouts, for things related to spanning in this particular case. There's a threat mechanism that I'll talk more than you'll probably want to hear called vortex-induced vibration, and I'll get into that in a bit. But what that involves is in the case where you have a pipeline that's spanning, it's unsupported in the presence of water current, what can happen is the water current can cause oscillatory vibrations to set up in the pipeline. And if you approach a natural harmonic frequency of the pipeline over that span, you get internal feedback, and ultimately, simply put, it can shake itself apart. It can, over a longer time frame, erode the fatigue life of the pipeline. And that's really characterized under weather and outside force. That's part of that category. And the last is in some respects, captured in a few other of the threat mechanisms that have already been discussed, and that's activation of resident damage from pressure cycle-induced fatigue. The one thing about liquids pipelines is that liquids inside the pipelines are incompressible, and in that respect, they're different. It's a different setup than a natural gas pipeline. Natural gas, the product inside the gas pipeline, is compressible, and as a result, we don't tend to have such strong fatigue environments going on in natural gas pipelines as you can have in liquids pipelines. So it's important to assess the fatigue, the fatigue characteristics of the operations of the pipeline, particularly in the case of liquids pipelines. So the threat assessment approach for every one of these threat categories involves certain sets of data that need to be reviewed. For external corrosion, for instance, you need to review all those things that relate to potential for external corrosion to occur. So that includes the coating type, the coating age, any evidence of degradation. It involves cathodic protection, and I'll describe a little bit more about cathodic protection in a little bit here, but for the time being, cathodic protection is what pipeline operators use to help protect against corrosion on pipelines. What they essentially do is they hook up their pipeline to a rectifier. You can think of it as a large battery. You hook up your pipeline to the negative pole of the battery. You hook up the positive pole of the battery to a remote rectifier bed. It's not really a battery, by the way, but for conceptualizing how this thing works. Think of it as such. And what you try to do is you try to make the pipeline more negative than its native corrosion potential. And in so doing, if you do have holidays or gaps in the coating, the idea is that you help that pipeline be protected from corrosion. So that being the case, there's a lot of data to review in cathodic protection. There's cathodic protection readings, there's rectifier readings, and so on. And above all, there is, in reviewing all of these threat attributes, there's inline inspection data. And on Enbridge Line 5 in the Straits of Mackinac, the straits have been inspected every 5 years with metal loss tools since 1998, I believe, is the number. And so it'd be just prohibitive to put all the inspections on one slide, but the later inspections are those inspections that are of more interest in any case, because those inspections are done with more modern tools, and they give you a better idea of the actual state of the pipeline currently. And inline inspection is basically what it involves is loading an inspection tool into the pipeline, and these things are like robots. They are semi-autonomous robots, and they go through the pipeline and they collect data that the hardware and software on board tells them to collect. There's a variety of tools that do a variety of inspections using a variety of technologies. But for the purposes of this discussion here, I've characterized them in terms of 6 different tools that have been run since 2008, 6 different types of tools. The first type is something called magnetic flux leakage, and that's a tool that's designed to find metal loss. The way it works is that it induces a flux of magnetism in the pipe, and in any local area where there's metal loss, what happens is that magnetic flux leaks out of the pipe wall and is detected by sensors called Hall effect sensors. And it involves a lot of physics, but the interpretation of the signals on those Hall effect sensors enable you, with a fair amount of reliability actually these days, to measure the location and the size of the metal loss. Not only that, but whether that metal loss is on the inside of the pipe or on the outside of the pipe. So essentially the length, depth, and width of the metal loss. There are geometry and caliper tools, and those are tools that are designed with mechanical feelers to identify dents. It's a lot less sophisticated perhaps than other types of tools because it's got mechanical feelers on it, but it does a very reliable job of identifying where dents are, ovalities are, and the sizes of those dents and ovalities. There are ultrasonic circumferential crack tools, and those use ultrasound technologies to detect cracks oriented circumferentially. There's a tethered time-of-flight diffraction phased array tool. And by tethered tool, what I mean is that this is not what we call a free-swimming tool. It's tethered to a cable. And in this case, what happens is that this tool goes along the pipeline. Every time it encounters a girth weld, it stops, and it inspects the girth weld with two types of ultrasound technologies. One is called time-of-flight diffraction, and the other one is called phased array. After that, I can't see. The next type of tool is a cathodic protection current mapper, CPCM tool. What that does is it enables, I talked earlier about cathodic protection and how you're trying to broadcast current onto the pipe, creating the pipe in a more electronegative environment. What this tool does is it goes along the pipeline, and all around the circumference of the pipe, it can identify areas where current is either arriving at the pipe or leaving at the pipe. And in so doing, it does a couple of things. It identifies where you have local areas where current is arriving at the pipe, it tells you that, that you've got a gap in the coating there, and that current is arriving at the pipe from the rectifier. So although you have got a gap in the coating, you're protecting that gap in the coating by the rectifier. It'll also identify areas where current is leaving the pipe, and that is really the thing that you're really concerned about, because not only do you have a gap in the coating, but it's actively corroding. Current is leaving the pipe. So this does two things essentially. It establishes gives you a picture of the integrity of the coating, plus it identifies where current may be arriving at or leaving the pipe. The final tool category is a acoustic leak detection tool. And what it does is it looks like a small beach ball, and it goes through the pipeline, and it is designed to pick up acoustic emissions that would be associated with even very, very small leaks. A leak rate of about a half a cup a minute would be sufficient to be picked up by this tool. So these are the sorts of information, along with material grade information, the construction techniques information, the material property information, and so on, that we had to integrate and evaluate as part of the threat assessment. And at the end of the day, we identified three major categories of principal threats, three major categories involving 4 threats. The biggest threat was immediate failure due to mechanical damage, and specifically anchor interaction. One of the things that we noted when we were going through the records is that when the pipeline was being contemplated back in 1952-53, that the Great Lakes Shippers Association expressed great concern about the location of the pipeline sitting on lake bed through the channel of the Straits of Mackinac. They expressed that concern because they felt that there is a potential for inadvertent anchor hooking. And as it turns out, when we did the analysis, that actually was the most significant threat. And we'll talk about how that all developed and the findings associated with that. The next threat that was characterized as a principal threat is incorrect operations. So again, the potential for somebody to make an inadvertent error or mistake that leads to a failure on the pipeline. And finally, we identified 2 sources of spamming-related threats that come under the category of weather-related and outside forces. And one was, again, vortex-induced vibration, and the other one was simply overload or overstrain due to spans. And there are a couple of forces that you need to consider when evaluating spans. One is simply gravity, the other one is drag due to current. Now, those far and away outweigh all other threats combined, orders of magnitude above, to the extent that the other threats are unquantifiable. They're unquantifiably low. And I'll talk about a couple of them because I know that I've read concerns about things such as external corrosion, for sure, and I want to talk a little bit about that. So the reason why we didn't identify external corrosion as a principal threat is, again, that compared to the combined threats of the principal threats, the potential for failure is extremely low. And we arrived at that conclusion by integrating a lot of information from the inline inspection tools. So again, high-resolution magnetic flux leakage inline inspection every 5 years, and we evaluated all of those inspection data. What we discovered is that there is no evidence of any external corrosion wall loss at all on either of these 2 pipelines. And in terms of an onshore operating pipeline, that's a little surprising because onshore operating pipelines do have regularly, they have at least some external corrosion going on. As it turns out, offshore pipelines such as these tend not to be problematic with respect to external corrosion, and the reason for that is that the offshore environment is actually pretty easy to deal with from a corrosion protection standpoint. Onshore, by way of comparison, you've got a lot of challenges. You've got an inconsistent environment that the pipeline is existing in. Sometimes it's wet, sometimes it's dry. When it's wet, the soil swells. When it's dry, the soil shrinks and cracks. It works away at the coating, creates a lot of coating holidays. Furthermore, the dry zones during the dry periods do not broadcast, they don't transmit cathodic protection currents. And so you could have potentially a pipeline sitting in the bottom of the pipeline is wet, but remote to that, the ground is dry. It's getting inadequate cathodic protection, and so it's going to corrode. So by comparison, offshore pipelines are in a very uniform environment. It's uniformly easy to transmit cathodic protection through the environment and to do it very effectively. And you don't get that wet and dry cycling and soil stresses that promote decay and degradation of the coating. With respect to the coating, it is what we would characterize as a vintage coating system. It's a coal tar enamel coating. Although vintage, it actually doesn't have that bad a performance record. They ultimately went away from it in favor of what are called thin film epoxy coating systems in around 1980 timeframe. But based on the CPCM in-line inspection tool that I talked about, the cathodic protection current mapping tool, that is a very effective tool at identifying what are called coating holidays or gaps in the coating. And there were actually no current anomalies that would be indicative of those sorts of gaps in the coating. And the conclusion for both the east and west pipelines from that inspection were that the pipeline coating is actually in excellent condition. That's at odds with the opinion you would get by simply looking at the video image of the pipes sitting on the bottom of the lake bed. Because you can see physically there's something, you can't quite define exactly what it might be, but it looks like something might be detaching from the pipeline. In my personal experience with coal tar epoxy coatings, and I have to say it's fairly extensive experience, the outer wrap, which is variously either craft paper wrap or asbestos felt outer wrap, is prone to detachment from the underlying corrosion coating, which is a coal tar base, and that is really the underlying coating is the thing that is the corrosion coating. The outer wrap is not. So it could well be that what people are seeing on the underwater inspections is in fact the outer wrap. So that's in a nutshell, why corrosion, by way of example, was assessed as being of low potential relative to the other threats. Now I want to make it really clear here that just because this one threat was characterized as being low, it's being characterized as being low in relationship to the dominant effect of the other threats. So it doesn't stand that we're necessarily saying the probability of failure is low just because this one threat is low. So I don't want to leave you with that notion. So getting to the dominant threat of anchor interaction. There is some history behind this threat in other jurisdictions, most specifically in the North Sea, where failures and incidents have occurred associated with inadvertent anchor drag. And so what really happens is that there is a possibility of a variety of scenarios by which a ship that is underway can inadvertently deploy its anchor and either recognize that it has inadvertently deployed the anchor quickly, and then hopefully do something about it quickly, but in the meantime, you've got a dragged anchor for a period of time. Or otherwise, they may not be aware of it. We followed the standardized approach, which is, the guidelines are called unintentional anchor drops from ships underway, and it's specifically geared to evaluate this particular threat. The image on the left here is schematic of what we are talking about here. And what you can see is initially on the top, let's see if I can work this in. On the top schematic here, what we've got is a chain, a shank, and you've got flukes that you can't quite see, but as the images come down, you can see that the flukes are now penetrating into the sand. And the potential here, the threat is that you can get a pipeline lodged in between the flukes and the shank. And the fact of the matter is that you can't stop an 80,000-ton cargo vessel with a 20-inch pipeline. So that's the concern. It's sort of a random threat. It's not really related to the age of the pipeline or the material properties of the pipeline. It's really related to the design and installation of the pipeline. The pipeline is sitting on top of lake bed below a busy shipping channel. And so you could replace that pipeline with a brand new pipeline, put it on top of lake bed, and you're not going to materially affect the probability of failure associated with this threat. So the way we evaluated this is, first of all, we need to get an understanding of the traffic density through the straits. Obviously, smaller vessels may have smaller anchors, and they would also have lighter chains, not capable of breaking a 20-inch pipeline, whereas larger vessels would have bigger chains, they would have bigger distances between the shank and the fluke that could actually accommodate a 20-inch pipeline, and the chain strength would be great enough to break the pipeline. And it all depends on shipping class or the displacement of the vessel. And so we need to get an understanding of what kinds of ships are going through the Straits of Mackinac, how big are they, and what frequency are they going through. That was central to the whole investigation. Unfortunately, there's information on that. There's the nationwide automatic identification system, and it's based on UHF receivers that are located at various locations throughout the Great Lakes, and fortunately, they are located in such a position so that we can get an accurate representation of shipping traffic through the straits. Those receivers record not only the frequency with which the shipping goes through the straits, but it identifies information related to each ship that goes through. It gives us an MMS number, or basically a ship identification number, which enables us then to look up in a separate database, okay, what's the displacement of the ship? And from that, you can infer things such as what's the chain length, what's the chain strength, what's the anchor size. And these are all related to the process of investigating this. There are two failure criteria that were investigated as part of all of this. One is simply overstrain. So if you happen to hook that pipeline, fit it in between the flukes and the shank, and you pull on it, ultimately you create a plastic collapse situation. The pipeline pulls itself apart. That's one. The other one is critical dent. So it's feasible that the anchor could create a dent on the pipeline that's big enough to create a failure before you reach that critical strain. The minimum force required to either reach a critical dent or an overstrain is what's characterized as the critical force. And you compare that critical force against the chain break strength, essentially, to come up with whether or not that particular ship can give rise to failure. And of course, the analysis has to also consider the chain length relative to the water depth. These waters here, though, are quite shallow in relationship to cargo vessels' chain lengths. So that really wasn't a big factor in the analysis. Incorrect operations is a mechanism for failure. It's also fairly random. It doesn't really enable itself, it doesn't lend itself to statistical analysis. There is no mathematical model that predicts failure due to incorrect operations, which would enable us to do a reliability method analysis on it. We had to instead look at the hazardous liquids incident database that is published by the U.S. DOT's Office of Pipeline Safety. It's the Pipeline Hazardous Material Safety Administration database. And looking through that database, we can get, for similar installations, what's the likelihood of having a failure due to this particular threat, and that's what we did. For vortex-induced vibration, and I don't want people to panic here when they see this, but the message is fairly straightforward. Again, we rely on existing industry standard practices to evaluate this threat. And what happens, again, with vortex-induced vibration is that a span of pipeline that's being exposed to a current can set up a turbulence. And every time a piece of turbulence gets shed off of the trailing edge of the pipeline, it sets up a vibration. And that vibration becomes more pronounced as you get a span that is a span which, in conjunction with the evaluation of the diameter and the material properties, causes it to vibrate at its harmonic frequency. And when that happens, the fatigue life can become quite short. The important thing here is that this evaluation is a function of, and I'm not going to walk through these equations except to say that they are a function of span length and water current velocity. So V and L in these equations. So the challenge now is, okay, I know what diameter the pipe is, I know what the wall thickness is, I know what the material properties look like. I even know certain things such as, well, it has zebra mussels on it, so therefore those zebra mussels impart a certain characteristic drag coefficient that I know that I need to take account of. But I need to know what's the span length, what's the water velocity, and furthermore, I need to know not just one single span length and one single water velocity, but I need to be able to express those as probability distributions, because there is no single span, there is no single water velocity. And so what we did is what engineers do all the time when faced with this sort of situation. There are buoy data that are in the straits that give us an understanding of current velocity through the depth of the water column. But there's only a few of these buoys. They're not at every location along the existing east and west spans. Ideally, I'd like to know that. I'd like to know what the current velocity is close to the bottom of the lake at every location along the east and west spans. And furthermore, I'd like to know what are the span lengths. One of the advantages of having done a comprehensive evaluation here is that it involved a three-dimensional hydrodynamic model that Dale is going to get up and talk about a little later on. And what modeling does is it fills in the gaps where the data don't exist. And engineers rely on this sort of thing all the time when they build bridges, for instance, across the Tacoma Narrows. Normally, in order to do a good job of building that bridge and ensure that the bridge doesn't fall down, I need to know what the wind velocity is, not just today, not just last week, and not just at one location across the Narrows. I want to know it at all locations across the Narrows. And I need to know it over a large period of time. And what they do in that case, of course, is they develop a wind model, and they use that to help design the bridge. Similarly, if you want to build a building in San Francisco, rather than wish that you had 20,000 years of seismic data, you have seismic models, and you can model what the expected frequency and magnitudes ground vibration are going to be. And so this is what we did here as well. We used the output of the 3D hydrodynamic model to model the temporal current velocity. By that I mean the current velocity with time, how it changes with time along the entire existing crossings of both the east and west pipelines. And we picked the upper bound, the highest current velocity that existed at both the east and west crossings, and evaluated how that current velocity at those locations, those most critical locations for current, changed over time. And we developed a probability distribution here. And this probability distribution is shown on the left. It's shown for the west segment, but we developed a separate probability distribution for the east segment as well. What that enables us now to do is to say, okay, what's the full range of possible current velocities that might come to bear here? And what's the probability associated with any given current velocity? It's open-ended. There's no upper bound to this. These distributions, although these, by the way, these units that are shown in this probability density function are in meters per second. They are in meters per second because that's the data that those are the units that the data were gathered in. But although the units on this graph go up to, the graph only goes up to 0.3 meters per second, but that doesn't mean that we didn't evaluate velocities that are beyond 0.3. Quite clearly, looking at the shape of that graph, there's a certain probability that you could have a current velocity of 0.6 or 1 or even greater. And so that's the beauty of doing it this way, is it leaves you open to the possibility of having a broad range without any upper bound of current velocities. Similarly, on the span distribution, we developed a distribution for span length, and for that, we leveraged span inspection data that exists between 2005 and 2015. And you may be aware that as part of the easement agreement, the span length is required to be less than 75 feet. You may also be aware that hasn't always been the case. And in fact, when we went through the data, we found spans of up to, I think, 130 so feet. So well in excess of the 75 feet that are associated with the easement agreement. We used the existing data, made the assumption that what was observed during this past time frame would occur on a go-forward basis, that we would continue to have large spans, and we built a probability distribution from that. We then, having expressed these variables as random variables that can be described as probability distributions, we then inputted those variables into what's called a Monte Carlo model. A Monte Carlo model is just a way of being able to incorporate variables that are not single discrete variables, but rather probability density functions. And what you have to do is you randomly select, every time you run a Monte Carlo simulation, you randomly select variables from these probability density functions, and you calculate, in this case, the number of years to failure. And you do that over and over and over again. It's kind of like throwing the dice, and that's where the name comes from. Monte Carlo is a European casino. It's a famous place where they have games of chance. And so it's a little bit, mathematically, it's like throwing the dice, and we threw the dice, in this case, 100 million times, and came up with a probability for failure associated with vortex-induced vibration. Spanning is a separate calculation that we did, and again, this one's a little bit different in that what we're really looking at here is the potential for overstrain. Although there is a potential for overstrain due to gravity as well as due to drag, because we've got water current. Those aren't the only forces that we needed to evaluate. There's also temperature differential, and there's also something that's related to operational stresses. Basically, when you pressurize a pipeline, the pipe wants to get bigger in the circumference, and due to conservation of volume considerations, as it gets bigger in its circumference, it also wants to get shorter, but it can't because it's tied in at either end, and so it sets up an axial stress, and that's referred to as Poisson stresses. And so we looked at temperature stresses, Poisson stresses, gravity stresses, and temperature stresses. And the spanning stresses, of course, are going to be a function not only of span length, but also of water current, because we're considering drag. And so we were able to use those probability distributions on span length and water velocity. Again, throwing it into a Monte Carlo simulator and running the Monte Carlo engine again 100 million times in order to come up with the probability of failure. When I say failure, I need to define what I mean by failure for this particular case. If you take a piece of steel and you pull on it, you will find that as you pull, it will stretch. And the more you pull, the more it will stretch. And the relationship between force and the amount that it stresses is proportional. If you pull twice as hard, it will stretch twice as much. And it's proportional up to a limit, and that limit is called the proportionality limit, or it's also known as its yield strength. And this chart here, that depicts the stress-strain relationship, or in other words, the pull versus stretch relationship for steel. And what it shows you is that it's a very steep curve on this graph, that you've got a linear relationship. Again, the more you pull, the more it stretches in a proportional manner, up until what's called the yield point, at which point, if you pull more beyond that point, the material is going to stretch permanently, and that's called yielding. And this point here is, in terms of stretch, it's about 0.2%. 0.2% stretch is the proportional limit for steel. It's defined as the yield point. You can see that the actual failure point, the point at which plastic collapse occurs and the metal breaks, is well beyond that 0.2%. It's way out here, somewhere around 20%. So if you were to pull steel on a one-time basis, this would define the point of failure way out here. We did not use that as the defining criterion for failure. Instead, we used yielding way back there as the defining point. And you may ask why, because that's obviously what I've just finished telling you is that failure does not occur there. But what does occur is that that sets up the opportunity for high amplitude fatigue. And you have to realize that the environment down at the bottom of the straits we had to consider that to be a dynamic environment. Currents change, span lengths change over time. And so if you can yield the pipe on a one-time basis, you have to assume that you can yield it on more than a one-time basis. And if you can do that, it sets up a situation where the pipeline can suffer from what's called high amplitude fatigue. So it's a conservative failure criterion, but a failure criterion that we applied. This may be getting into perhaps more detail than you may want to know, but this stress-strain relationship is what steel looks like if you pull it in a single direction. But in actual fact, the stress state in the pipeline is what we call biaxial. The stress is circumferential as well as axial, and there's a yield criterion that we had to investigate because of that. Because if you compress steel in one direction and simultaneously stretch it in another direction, its yield point in that other direction is actually suppressed. So you need to consider that. And so what we had to do is we had to consider a variety of combinations of product density and water depth, because, and we considered all these different combinations so that we could pick the combination that gave rise to the earliest onset of failure. And that's what we did. I'm just going to have a look at this. Okay, sorry, just timing of the break. I understand we're going to take a break after I'm done. So, in summary, spanning-related threats, there were two. One is vortex-induced vibration. One is overstrain due to unsupported span lengths. After running 100 million simulations on the vortex-induced vibration analysis, we came up with a range of failure likelihood. And because failure is related to fatigue, it's a time-dependent failure mechanism. So the probability of failure ranges from the year 2018 to the end of our analysis period, which we picked as 2053, 35 years from now. And it ranges, it increases actually fairly slowly over that time period. It only increases by about 3.5% over that time period. These are the numbers for those of you who are interested. I can't see. So the probabilities of failure expressed in scientific notation: 1.42 times 10 to the minus 5 in the year 2018, rising to 1.61 times 10 to the minus 5 in the year 2053. In the case of overstrain analysis, after running the simulation 100 million times, we found that the probability of failure due to that mechanism was actually below our ability to detect it. So very, very low in that case. That's, in theory, what the model says. But so we had to double check and make sure that bore out by evidence. And so what we did is we looked at 2016 inertial mapping unit inspection data. And so the IMU tool is not a tool that I've described before, but it has onboard gyroscopes, and it can identify deviations. It can identify bends along the length of the pipeline. And Enbridge has run IMU tools in 2016 as well as in, I'm not sure if I've got it mentioned here, a previous time period, which I don't actually recall, but what we were able to identify is that there are, in the east segment, 20 bends within detection capability of the tool. Only 2 of those are in the untrenched portion of the Straits crossing. The rest of them are in the section which is buried. On the other pipeline, on the west segment, there are 23 bends, again, 5 of which are in the untrenched portion. So there seems to be bends in this pipeline, but the vast majority of these bends appear to be in the trenched portion and away from the spans. So it looks, on the surface at least, that these may be bends that were associated with installation. However, what we did, and here's the date of the previous tool. There was a previous IMU inspection in 2003, and so there was a comparison of bends as identified in the 2003 inspection made with the bends made in the 2016 inspection, and the bends that were there in 2003 were the bends that were there in 2016. There was no growth in bends. So it doesn't seem like these are bends that are being developed over time. There were 2 bends on the west segment, by the way, that were within 3 feet of the girth weld, and so for cross-reference purposes, what we did, I mentioned the tethered tool, the tunnel flight phased array tool that inspects welds, girth welds. We went to those 2 welds where the bends were close to, and we had a look at the girth welds to ensure that, the concern was that has a bend occurred that might have compromised the quality of that weld, and there were no girth weld anomalies at those welds. So that seems to support the analysis, the strain analysis that we performed. So I've gone on here a little bit, I'm afraid, but this is the sort of threat assessment and failure probability assessment that we performed for the pipeline. At the end of the day, what we ended up was a probability of failure for each of the principal threats. And the combined probability of failure for all threats that we established between now and 2053 is about 1.6, about 1.6%, so about a 1 in 60 chance, really, of having a failure in the straits between now and 2053. And again, we've been asked specifically not to weigh in on whether we feel things are high or low, or to offer opinions. They are what they are. By the way, the time-dependent component of those threats is very marginal. The only time-dependent component is that which is due to vortex-induced vibration, which is shown on this graph as the dotted blue line. And you can't even really see the slope to that line. There is a slope, but as I mentioned earlier, it increases over the time frame by only about 3%. So the things that can give rise to failure are random threats. They're attributed really to the design of the pipeline and not attributed to degradation mechanisms by and large. And that's an important finding for the evaluation of the safe operation of life. Some pipelines, the threat mechanisms on those pipelines are dominated by time-dependent threats. And in those cases, the probability of failure increases. It may increase non-linearly with time, and the challenge is to draw a line and say, beyond this point, we can't live with this threat. Often operators try to manage those threats by inline inspection and pig and dig strategies. There are some threats that don't lend themselves well to that, and so that discussion comes into play when evaluating the operating life. So the other thing that needs to be addressed is, okay, those are the threats. What about the material properties of the pipeline? This is made of steel. Is there something intrinsic about the properties of steel that change over time that will make this pipeline less robust, less susceptible to failure, or more prone to failure over time? And the bottom line is, steel properties really don't change significantly from the perspective of practical limitations to operating pipelines. Steel properties can change at high temperatures and under certain circumstances, but for the application of pipelines, they don't change over time. So getting back to an evaluation of operating life, the operating life or the suitability for service has to be dictated in terms of its deemed risk acceptability at this point in time. I would say that the time component of degradation isn't going to be the thing that drives that decision. You need to look at the failure likelihood, and the things that are giving rise to that failure likelihood are not degradation mechanisms, they're random threats. The suitability for continued service that is, I guess, your collective task to arrive at is going to be dictated by these random threats. So again, I just need to caution that just because time-based degradation mechanisms aren't the thing that is driving the failure probability in this pipeline is not to say or make any assumption or pronouncement on suitability. Pat, you passed me a note about Yep. Is this a place that you want? Okay.
Okay, Jim, that's a good stop?
Yep.
Perfect. Okay, I know this is really complex and very technical, obviously. These engineers, when they get talking, I have a whole pile of them on my staff. You can't get them to stop because they're very excited about the topic. And that shows in the presentation. There's a lot of really important information in here, a very detailed report, which I encourage you to go out and read and look at so that you can provide us with some great comments as we move forward in the evaluation of the report and make sure your comments and questions are incorporated. So right now we want to take a short 10-minute break. I assure you your questions will all be answered tonight, or at least we will get to you to get your questions asked at minimum. So we'll just take a quick 10-minute break. Get up, stretch your feet, take a biological break. We'll be back here in 10 minutes. They'll finish up and we'll start your questions. Thank you.
Alright guys, so we're going to come back live again in a little bit with the questions and answers. I anticipate it being quite an interesting question and answer session, so if you can come back for it, that would be perfect. For anyone who stuck with this while it was on, I know it was a little dry, and appreciate you being here. Please share it out. I'll save my comments on this for now, but we'll do a live stream later on, and I'll talk more about my thoughts about this. Much love to you guys. Thanks for watching.